Welcome back to lecture 5.5. Lecture 5.5, where we have just finished discussing the three-dimensional coefficient of thermal expansion, and then we discussed the three-dimensional bulk modulus, and the isothermal compressibility, which is 1 over the bulk modulus. So now I think we have all of the components we need to define our equation of state, our three-dimensional equation of state for a solid or a gas. Okay? So the first step is realizing that in many of the occasions what we really wanted was to understand how the volume changes, right? So when PV equals nRT, we could rewrite as how the volume changes with pressure and temperature. Okay, so we're going to write the equivalent for three dimensions. We're going to want to know how the volume changes with pressure and temperature. That's like how the one-dimensional one, we had the length depended on force and temperature. Okay? So very generally, we want to know how the volume depends on pressure and temperature. And we can just simply write down the equation of state, in essence, which was partial V, partial T, a constant P, dt, plus partial V, partial P, a constant T, dP. Okay, so we've just thrown this out there, right? We've just gone straight almost to the answer. So how did we get to such a thing, right? How did we do this? And you'll see that some of these terms, dV dt is going to have to do with the coefficient of thermal expansion. dV dP is going to have to do with the compressibility, right? So we're going to have our equation of state in terms of those things. So how did we know to simply write this down? How could we simply just write down this equation out of the blue? Well, this comes from the math of partial derivatives. Okay, so let's take a small exploration into the math of partial derivatives. So imagine that we have two variables. Let's call them x and y, right? So they're going to be orthogonal. We're going to plot, say, p and t. They're the two variables, and we're going to ask, how does a function f depend on x and y, right? So let's plot. So we're just gonna call that f, but we're gonna explore the function, how f depends on x and y. Okay. So imagine, for example, we have some point here, right? That it has some x and some y. There might be some f that depends on it, right? And so we can really imagine, for example, some function that lives in this xy plane, right? So we can really imagine having some point here that lived on a surface, right, in this three-dimensional space, right? So now that we realize that the function is how it depends on x and y, right? we can see how to geometrically think about these things independently, right? So I can imagine projections in the fx plane or in the fy plane, right? And so let's do that. Okay, so let's imagine for a fixed y, right? Let's look at how f depends on x. So we're going to just have this projection into the fx plane at some fixed y, right? So we're going to have how f depends on x, right? So imagine that we started at some initial point x, we had some point f, right? And this is, let's say, x plus delta x. So we're going to arrive, so this is f evaluated at x, and so maybe this would be f evaluated at x plus delta x. Okay? Let me just rewrite that so it's a little bit more clear. So for a fixed y, right? So this is the f plane, and this is f of x plus delta x. All right. Okay, so now you can see that f of x plus delta x is some line in this plane, right? So that's what I'm kind of drawing there. This is this and this, for example, right? So we know that if we take delta x to be infinitesimally small, right? Very, infinitesimally small changes in x, we can call it dx. And then this would be our infinitesimal change that's corresponding to that function in df, right? So if we want to say, what is df, right, evaluated at a fixed y, right? Well, that's simply the slope of this line, right, times dx, right? So if I want to know df, right, I'm basically saying what's the slope, df dx, and from that, multiplying that slope by dx, I can get df. Or another way to write that is simply that this is partial f, partial x, evaluated at y, dx. Similarly, for fixed x, right, df evaluated at x would simply be partial f, partial y, evaluated at x, dy. Sorry, partial f, partial y at constant x, dy. But again, those are both only independent, those are both chunks. So our total df, right, because in this function of two variables, we're really looking at a three-dimensional space here, right? So we really would need to know how it changed here and how it changed there to do both. So we simply can add them together. So this would be partial f, partial x at constant y, dx, plus partial f, partial y, constant x, dy. Perfect. And so that's exactly why we can just take our v, which is a function of p and t, and you see here the f is the v, the p is the x, and the t is the y. And we can get this exactly. Okay, so now let's keep that part and realize that now this part, partial v, partial t, so let's go back to our definition of beta, right? So beta was defined to be 1 over v, partial t, at constant p. So we can rewrite that as partial v, partial t, at constant p equals beta v. And let's see, what was our definition of B? Was minus V partial P partial V at constant T. All right? Partial minus V, partial P, partial V is constant T. That's right. And our kappa, our coefficient of, so this was thermal expansion, this was our compressibility, right? So kappa is our compressibility, was 1 over B, right? So that was minus 1 over V partial P. Partial V, partial P, constant T. Okay, so now you can see what we're going to rewrite this one to look like that. Partial V, partial P, at constant T is equal to minus kappa V. Okay, so we're going to take this part and this part, right? And we're going to combine it with this part. Okay, so let's write that. Our dV is equal to, this is beta V dt minus kappa V dP. And now we have our 3D equation of state for a liquid or a gas. Okay, so what we're gonna stop there for lecture 5.5, and next time we're going to continue on. We're going to use this to look at the work. We're going to explore this three-dimensional equation of state a few times, and then we are going to calculate some work. Okay, next time.